the definition of a group, these group axioms up here. So the three of them presented here, although sometimes we like to say that there's 4 group axioms because the definition of closure, which is implicit up here in the definition of a binary operation. But for looking at certain groups, and certainly when we look at subgroups or groups formed by subsets of larger sets, sometimes checking the closure condition is non-trivial. You know, it does require a bit of checking. Okay? So that's what the pattern of a group is, and we looked at some initial examples. And so for today, we'd like to discuss some of these groups on basic properties of groups. Now, the proofs are laid out in the notes, but I just thought I'd go through them on the board to just discuss some aspects of them, and we can see the way the various axioms kind of link together to give us the results. Okay? So, and as we go through this, you know, please, any questions or queries or things you're unsure about the way the arguments are working, do stop me and ask. Okay? So first basic thing, the identity in a group is unique. Strictly speaking, there's nothing in the group axioms that kind of says that the identity has to be unique. And when you first look at it, you know, maybe conceivably in a system like this, there might be more than one identity floating around, more than one special element, such that when you multiply it by another element, it doesn't change the other element. And that's not to say that you can never have more than one identity for a binary operation, but it's when you have the other properties, when you have the associativity really is the key. Associativity and the other properties together imply that you can't really have more than one identity. Although no, it doesn't really hinge on. Anyway, let's talk through. So this is that the identity is unique. So the way the proof works here is to suppose that there are 2 identities. Suppose we do have 2 identities, E1 and E2. Well, the basic idea here is to consider the element E1 times E2. If there were these 2 identities floating around, these 2 elements, such that when you multiply it by any other element, it leaves it unchanged. What about when you multiply the 2 of them together? What's that going to do? Well, you see, on the one hand, E1, E2, we can focus on the fact that E1 is an identity. So disregarding for the moment what the other element is, E1 is an identity. So when you multiply it by this thing behind my hand, it has to leave it unchanged. So certainly this must be equal to E2. Okay, because E1 is an identity. But also, E1, E2, now you look at it the other way. Disregard the first element for a moment. And here we focus on the fact that E2 is an identity element. So therefore, when you multiply E2 by whatever this is underneath my hand, it leaves whatever that is unchanged. So actually, sorry, it doesn't turn on associativity or anything. It just turns on the basic idea of an identity element, that the identity element has to work on both sides. And if it does work on both sides, an identity element, we're forced to conclude that this element, which is E1 times E2, this is in fact equal to both of them, so therefore E1 must equal E2. Okay? So you can never have 2 different identities floating around. If you think you have 2 different identities floating around, really you just applied 2 different labels to the same object. So it is the same thing. That implies E1 equals E2 just by the principle of equality. So identities are unique. Now, when you look at even more basic algebra, sometimes you consider left-handed identities and right-handed identities, or identities that act on the left and identities that act on the right. And maybe in some of those much looser systems, you might have more than one identity on the front. Proposition 3.118 says a similar thing for inverses. Now, there's no proof there for that in the book, so that is left, isn't it? Or is it proved in the? Yeah, it's proved in the paragraph beforehand, but we might summarize it. Again, very similar approach. We'll consider any group element and let's suppose a H1 and a H2 are both inverses for G. Okay, so I'll pretend for the moment that I've got G. It's a very similar argument, except here the correct thing to consider is the product of three elements, H1, G, H2. And here this is turning on associativity. By associativity, I know that this product of three elements is referring to a unique element. It's not ambiguous. Okay? Strictly speaking, in order to evaluate such a product, I have to either first multiply H1 by G, then multiply the result by H2, or I have to first multiply G by H2, then multiply the result from the left by H1. But associativity, because this is a group, the operation is associative, so we know it's that this triple product is a unique element. And then on the one hand, we know that we bracket it up like this. So we now know the identity element is unique. So H1, H1 is an inverse of G, so when you multiply it by G, you get the identity. And identity times H2 just gives us H2. And when you bracket it the other way, H1 times GH2, you get H1 times the identity on the right, because of course H2 is also an inverse for G. And then we're getting H1. Okay. But by associativity, these two expressions are the same. They denote the same group element, so H1 and H2 must be the same group element by the principle of property. By associativity, H1 equals H2. Another thing to notice here is remember when we looked at when he presents the group axioms in the book, he's using that circle for the group operation. So, but it's quicker and nicer and more compact. Strictly speaking, I should be talking about some abstract group G with an operation circle, and there should be a circle in between all these elements here to denote the operation. But what we're doing here is we're dispensing with this symbol for the operation, and we're just writing things multiplicatively. So we're just using the common notation we would use if these were real numbers and we're multiplying them. You just write the real numbers beside you write the labels beside each other. But we're not saying these are numbers; these are just abstract values. Is that okay? Any questions about the way we're using the axioms there? I'm not laboriously saying axiom 1, axiom 2, blah, 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 but you can see that the principles being used there, associativity, the definition of the action of the identity, definition of the action of the inverses, those are the things being used. And so then you got some more similar results. Proposition 3.19. If you've got two elements, yeah, that's worth looking at. You've got two elements. The inverse of their product is the product of the inverses, but in the opposite order. Now this here, you should be very, very, very familiar with this. This is true in general for any binary operation where inverses are defined. And you've got to use this all the time when you're doing matrix computations and so on, and working with compositions of functions and so on. Well, the way it's proved is just simply by showing that it meets the definition, and that can be done by using associativity. So just the proof is, show it. So by it I mean this product on the right. Show it fulfills the definition of the inverse of AB by using associativity. Associativity. So here's AB. If we multiply it on the right by B inverse A inverse, if this is going to be the identity of AB, this should all come out to be if this is going to be the inverse of AB, this should all come out to be the identity element. And you can just see that it just takes a few applications of associativity. See, at the moment, we've got these two elements bracketed here, and some other element here, which is B inverse A inverse. So we want to move these set of brackets to over there. It's going to be A into B into B inverse A inverse. But then associativity again to shuffle the brackets around in the middle. This is going to be A into B inverse A. See, now we've got the B and the B inverse explicitly multiplying each other, so it's going to be the identity. Then the identity is going to be multiplying A inverse, it's going to leave A inverse unchanged. Then you're going to have A by A inverse, which gives you the identity. Let's go this all the way back here. This is A identity A inverse, which is A inverse, which is identity. Again, I'm not going to write out each explicit reference back to the axioms, but you should appreciate that each step there is justified by one of the axioms. Okay? Here, overall we're trying to test the definition of what the inverse of AB is. So we're claiming it's this, so we're trying it out. We're multiplying AB by this, and then each step is associativity, definition of the inverse element, definition of the identity, and definition of the inverse. Now that's when we multiply AB on the right by B inverse A inverse. Similarly, similar chain of equations. Similar chain of equations will show that when you multiply, B inverse A inverse by AB, put it on the left, that this is also okay, just exactly the same moves, just acting on the other side. To 3.21 and 3.22, I haven't stuck to the proofs of those, but let's just look at these. These refer to a cancellation law and a way to solve basic equations. So these simple equations, A times something equals B, or multiplying this unknown on the right by A, these always have unique solutions. And of course, what's the solution? Say for the first one, what's X going to be? Sorry? B over A. B over A, except avoid saying over A. That's quite not the right terminology for here. B divided. So when you're saying over A, you're thinking of numbers, but in the group theory context, you should say A inverse. Well, which product exactly for the first equation? What is X equal to for the first equation? A inverse times B. So A inverse on the left and B on the right. Yeah, because you got to multiply this on the left by A inverse to reduce it to X, since you got A inverse B. But for this equation,
Oh, B inverse.
B A inverse, yeah. So it's B on the left and A inverse on the right. Can you appreciate that? Yeah, yeah. So what we're doing there is, because remember, a group is not automatically abelian. So an abelian group is one where the operation is commutative, and we don't need to distinguish between A inverse B or B A inverse. They're both the same thing. That's the case in an abelian group. Abelian groups are special. They're much simpler than non-abelian groups because they do have this property that products are always, you can always flip the order in products. But in general, you can't. So in general, we need to take care about, when we're doing algebraic moves like that, simplifications like that, which side we're operating on all the time. And we've got to do it on the right side. Proposition 3.22 is a kind of like a cancellation principle. If you've got an equation and there's an A on the end of both equations, you can cancel it. And that will imply that B is equal to C. And similarly, when A is on the other side. Here's a question. Can you cancel, if you've got a product of more than one elements and there's an A on the inside, in the middle of the product, can you cancel out the A just simply from the middle of a product? So proposition 3.2. Let's suppose you've got an A, B, C equal to an E, B, D. Does this imply that AC is equal to ED? Can the B's be cancelled? Sorry, you can't see that. Can the, if you've got ABC equal to EBD, so you've got a B in the middle, can we cancel the B out from the middle? Now, the way the proposition, when you're just talking about a product of two elements on both sides, the way we reduce it, the way we cancel out is by multiplying both sides by the inverse of, well, in the previous case, A. So the only way we're going to cancel out B is if somehow we can multiply both sides by the inverse of B. But if you want to multiply this element on the left-hand side by B, you can multiply it on the left by B, you can multiply it on the right by B. You can't just, or well, we don't know. Are we free to just stick B into the middle? Well, strictly speaking, we're not. At the moment, there's a single element here, which is the value of this product, and we can put our extra B inverse on the left or on the right, and similarly for the right-hand side. So it's not so clear. I mean, you can try and move the A over. ABC equal to EBD, this does imply, say, that the BC is equal to A inverse EBD. We've multiplied both sides on the left by A inverse, so we've exposed one of the B's. And that would imply we could expose the B on the right-hand side by multiplying on the right by B inverse. We've exposed the B's, if you like, but they're on opposite sides of the expressions. So what we can't do here is multiply the left-hand side by B inverse on the left and multiply the right-hand side by B inverse on the right, because you're doing potentially, especially if it's in a non-abelian group, you're doing potentially different things to both sides of the equation. So there doesn't seem a way to. I mean, if the group operation is abelian, then yeah, we can flip pairwise products all the time. So we can flip the B to the left-hand side on one side, and we can flip and move the B to the left-hand side on the other side, and then cancel by multiplying by B inverse. But it looks like in a non-abelian group, it looks like that principle isn't available to you. And the B's, but you can expose elements that are in the middle, but the only way to do it is to force them to opposite sides of the expressions. So in an abelian group, we can cancel, could effectively cancel the b's, but not in a non-abelian group. Okay. Any questions on that? Theorem 3.23, the one at the end of this section, then establishes just some nice kind of notation. In a group, when we're writing the group operation multiplicatively like that, we can very easily give a definition to what powers of a group element are. So g raised to the power n, the natural definition is you're multiplying n g's together. And g to the negative n, when n is a positive number, that's going to refer, so this is just a definition of this piece of notation, that's going to refer to taking the inverse element of g and multiplying it by itself n times. And it turns out that the usual rules of indices do indeed apply. So these rules of indices that you're very familiar with when you're taking powers of numbers, they also work for taking powers of group elements. Okay? When you multiply a power of g by another power of g, so you've got some bunch of g's, n of them, multiplied by some bunch of g's, m of them, they're all g's. By associativity, it's unambiguous. How many g's do you have? You've got m plus n. So it's simple additive action of the indices there when you multiply. When you take a power of a power, that multiplies the indices. That's clear as well. We raise this element here to the power m. We're taking m collections of these, multiplying them together. How many g's in total? Well, if there's n in a group, it's going to be m times n of them there in total. And similar thing with passing minus signs in and out. So the GH raised to the power n is going to be the same as H inverse G inverse raised to the power minus n. And yeah, you see this rule here. Now this rule here, this looks suspect for a group in general. G times H to the power n, because what this means on the left-hand side is GH, 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 GH. Yeah, a load of pairs of GH multiplied by each other. On the right-hand side, we've got all the g's at the front and then all the h's. So that wouldn't be true in general, but if g is abelian, then all those pairs can be flipped in some kind of nice way to move all the g's to one end and all the h's to the other end. So if the group is an abelian group, this familiar action of an experiment takes place as well. Okay, then in the next section, they go through subgroups. Okay. Now, you may not realize it, but from your study last year you spent a lot of time studying subgroups, certain types of subgroups. You were doing it when you were studying vector subspaces, subspaces of a vector space. If you go back and look at the formal definition of a vector space, you'll notice that it's a type of group with respect to vector addition. Okay. I can't remember, was there maybe 8 axioms for a vector space? I can't remember. I think there's 4 axioms for the addition operation, 4 axioms for the scalar multiplication. If you look at the 4 axioms for the addition operation in the vector space, you see that they coincide with the axioms for an abelian group. So when you were looking at vector subspaces, that was exactly a smaller subspace inside a larger one. And that's a good example, or a good class of examples of this concept here of subgroups, which is just the same thing when applied to groups. So here's the definition here in the middle. When you've got some group G, a subgroup of G, we're going to call it H, it's a subset of G that acts like a little group with respect to the same operation that's going on in G. Okay? And it's part of the idea of talking about what the structure of the group G is. Part of that is talking about how many subgroups the group has inside it, and what the relation of all these subgroups are to each other, and so on. It's not always, so it should be emphasized that not any old subset of G will not necessarily be a subgroup. Okay? It's special behavior for special types of subset. There's a number of examples gone through here. And the key result at the end is these subgroup theorems, which give you, if you like, a way of testing various subsets of a group to see if they qualify as subgroups or not. Proposition 3.30 is basically just the definition of a group applied to the subset H. So H is a subgroup of G if and only if these three conditions hold. The identity of G is in H, H1 and H2 are in H, then their product is in H, that's the closure condition. And if H is in H, then H inverse is in H, gives the existence of inverses condition. What you notice here is that there's no associativity mentioned. So why isn't associativity mentioned? Associativity is part of the definition of a group. Well, if G is a group, then we know associativity works for all the elements in G. For every triple product of elements in G, it's unambiguous, and you can bracket it either way to give you the same thing. Well, since H is a subset of G, H is just some potentially smaller collection. It's just some of the elements from G. So associativity is a property of the elements. So if it works for all the elements in G, it's automatically going to work for all the elements in H. But that's the kind of key part of the proof of that, is just kind of talking about the fact that associativity automatically works. And then the last one is like a clever way of condensing these three conditions here into a much briefer form. It kind of combines the closure and the existence of inverses together in a neat kind of one-liner. Okay, so this condition here, proposition 3.31, is often the test that's applied to a given subset to establish whether it's a subgroup. So if H is a subset, it's going to be a subgroup if and only if, and really there's two conditions here. First of all, you have to be sure that it's non-empty. So that can be an issue when you define the subset, not by pointing explicitly to a bunch of elements, but by supplying some kind of condition on the elements of G. You have to be sure that the condition that's defining H is satisfied at least some of the time by some of the elements of G. And then we have this kind of combined closure and existence of inverses condition, and we're saying that this must be true that for all pairs of elements in H, so for every little g and little h that is in subset H, it must be true that the product of G and the inverse of H, written like this, G on the left and H inverse on the right, we have to be sure that that is also present in the subset. And if that is the case, then H is a subset. And the proof of this will be going through the steps to show that certainly these three conditions imply this condition in the statement in 3.31, and maybe the more important part is if the condition in 3.31 is true, then these three numbers 1, 2, and 3 of the previous proposition must be true as well. So the shorter paragraph is showing in the first direction. If you already know that H is a subgroup of G, you already know it's non-empty because it has the identity element in it, at least. And then if you take any pair of elements from it, if it's a subgroup, it's also going to contain H inverse. And it's a subgroup, so it must be closed. So when you multiply G and H inverse together, you're automatically in H. That's the quicker, easier direction. Slightly harder directions to show that if the statement in proposition 3.31 is true, then the three parts in the previous proposition, which are more or less the group axioms needed for the subgroup, that they must be true. And it's a clever little kind of trick here to get the existence of the identity. Because if you have this subset, we know it's non-empty. And we know that for every pair of elements, G and H in the subset, this product of G and the inverse of H is H. Well, if we know it's non-empty, then we know there is at least one element in G hanging around that we can point to. So there is some G around. Therefore, G times G inverse will be in H. Okay? Because what we're doing here is we're talking about the pair of elements G and G that are in H. Now we're mentioning the same element twice, but that's okay. This statement will apply. So we know that G and little g are in H. Therefore, the product G times G inverse will be in H. And of course, that product is equal to the identity. So that's how you get that the identity is in H. And then you have to show that for an arbitrary pair, H1, H2, then that's going to be in H. So that's the closure condition. But first of all, they proved that whenever you've got a G in H, its inverse element is also going to be in H. We've already proved that the identity is in H. So if we're focusing on some other element G, then we can use this condition here. So we got this G here as E, and the H is G. So if we know that E and G are in H, then E times G inverse will also be in H. But E times G inverse is just plainly G inverse. So then you know H contains all the inverses, and then it's going to contain H1, H2 for every pair H1 and H2 in H, because H1, H2 can be rendered as H1 times the inverse of H2 and the inverse of that. Because we know that H contains all the inverses, so if it contains H2, it will contain the inverse. And then because it contains H1 and H2 inverse, it will contain their product, which is H1 times H2. Okay. Okay, so that's good. We've seen some basic consequences of the group axioms. We've seen this definition of subgroups. So before the next lecture, I think what you should do is complete your reading of chapter 3. Read through those examples of subgroups, study these subgroup theorems that we've just looked at. And then, remember I said last time that there was plenty of space in these few weeks for working through these chapters 3, 4, and 5. So I think on Tuesday, see those exercises that I listed at the bottom of the reading notes for this week? I think we'll do like a good session on exercises, and we'll focus on some of those for the session on Tuesday. And also, since Mark raised it, that example with the Fibonacci sequence, maybe everybody try and solve that one as well, and I'll try and get that solved for Tuesday as well. Okay. So I'll see you in the lab session this evening. We're going to tidy up any issues from the previous lab session. As you see, we're going to maybe complete the work on the myGCD function so that it returns the necessary coefficients for the linear combinations equal to the greatest common divisor. And then there's a nice step-by-step tutorial on some of the group theory capability of SAGE here at the end of chapter 3, and then a guided exercise in section 3.8. Is that okay? Okay.